Jupiter and Saturn host strikingly different polar storms despite being similar giant planets, and scientists have long wondered why. New simulations suggest the answer may lie deep below the clouds. Spacecraft flybys have given scientists a front-row seat to some of the strangest weather in the solar system, especially over the poles of Jupiter and Saturn. Saturn's north pole is dominated by one giant storm that traces out a surprising hexagon, while Jupiter's polar region looks more like a tightly packed cluster, a central vortex ringed by 8 smaller ones. That contrast is hard to dismiss as a surface-level quirk. Jupiter and Saturn are similar in size and built largely from the same gases, yet their polar storms settle into very different long-lived arrangements. A team at MIT argues the answer may be hidden below the cloud tops. In work published in the Proceedings of the National Academy of Sciences, the researchers use computer simulations to watch orderly vortex patterns emerge from random churning on a gas giant. Depending on the conditions, the simulated winds either merged into a single dominant polar vortex like Saturn's or stabilized into multiple large circulations resembling Jupiter's. The key divider was a trait the team calls the softness of a vortex's base, which reflects a planet's interior composition. They describe each vortex as a spinning cylinder extending through many atmospheric layers. If the lower portion sits in softer, lighter material, the vortex hits a growth limit, leaving room for several smaller storms to coexist. If the base is harder and denser, the vortex can expand far more, swallowing nearby vortices until one massive system remains. That link between what happens deep inside a planet and the patterns seen from above adds a new twist to images returned by missions like Juno at Jupiter and Cassini at Saturn. If the model is right, the geometry of a planet's polar storms could act as a clue to what is happening beneath the clouds, where direct measurements are far harder to obtain. This study shows that depending on the interior properties and the softness of the bottom of the vortex, this will influence the kind of fluid pattern you observe at the surface. We don't know anyone's made this connection between the surface fluid pattern and the interior properties of these planets. One possible scenario could be that Saturn has a harder bottom than Jupiter. This new work was inspired by images of Jupiter and Saturn that have been taken by the Juno and Cassini missions. NASA's Juno spacecraft has been orbiting around Jupiter since 2016 and has captured stunning images of the planet's north pole and its multiple swirling vortices. From these images, scientists have estimated that each of Jupiter's vortices is immense, spanning about 3,000 miles across, almost half as wide as the Earth itself. The Cassini spacecraft, prior to intentionally burning up in Saturn's atmosphere in 2017, orbited the ringed planet for 13 years. Its observations of Saturn's north pole recorded a single hexagonal-shaped polar vortex, about 18,000 miles wide. People have spent a lot of time deciphering the differences between Jupiter and Saturn. The planets are about the same size and are both made mostly of hydrogen and helium. It's unclear why their polar vortices are so different. Researchers set out to identify a physical mechanism that would explain why one planet might evolve a single vortex, while the other hosts multiple vortices. To do so, they worked with a two-dimensional model of surface fluid dynamics. While a polar vortex is three-dimensional in nature, the team reasoned that they could accurately represent vortex evolution in 2 dimensions, as the fast rotation of Jupiter and Saturn enforces uniform motion along the rotating axis. In a fast-rotating system, fluid motion tends to be uniform along the rotating axis. So, researchers were motivated by this idea that we can reduce a 3D dynamical problem to a 2D problem because the fluid pattern does not change in 3D. This makes the problem hundreds of times faster and cheaper to simulate and study. What we see from the surface, the fluid pattern on Jupiter and Saturn, may tell us something about the interior, like how soft the bottom is, and that is important because maybe beneath Saturn's surface, the interior is more metal-enriched and has more condensable material, which allows it to provide stronger stratification than Jupiter. This would add to our understanding of these gas giants. Thank you for watching. If you've enjoyed our videos, subscribe to our channel for there's more to come.